One way to measure how a treatment group performed compared to their untreated or control peers is to use the control group to build a prediction model. We want to predict what midterm 2 score an individual might get based on their midterm 1 score in the control group, in this case among the students who were not mentored. Then for each student in the treatment group, we could come up with their predicted midterm 2 score, and we could look at their actual midterm 2 score. And the difference is how much they improved over what we expected them to get. That improvement, if it's positive, means that they outperformed their predicted score. And if it's negative, means that they underperformed their predicted score. And one way to quantify improvement would be to measure on average how much the individuals in some group outperformed the score that we expected them to get according to some kind of prediction. And here we have a scatter diagram. So one way we could perform prediction is using linear regression. But before we do that, we have to figure out, is this a linear association at all? So is linear regression appropriate? Okay, next we're going to look at just the students who did not receive mentoring. This is the control group. We're going to use this control group in order to figure out for each midterm 1 score, what's a typical midterm 2 score that you would expect a student with that midterm 1 score to get? Or what's the average midterm 2 score for that midterm 1 score? So that then all we need to know about a student is their midterm 1 score, 25, in order to guess at what their midterm 2 score might be. In this case, it looks like maybe 28. And perhaps we do this with linear regression. So here we've drawn the regression line through the same scatter plot, and we have to ask ourselves, does this look like a linear association? Are the dots distributed around the line? To me, it looks okay, except for maybe there's some effect here where most of the dots are below the line. How would we see that effect more clearly? Well, we draw a residual plot. So here's all the code that we developed during linear regression. Standard units, correlation, slope, intercept, computing the fitted values, the values along the line for each x. And the residuals are the difference between the actual y values and the fitted values. So how far above or below the line each point is. And then we can plot those residuals. We did that in an earlier lecture. And we'll plot the residuals for midterm 1 and midterm 2. So here are all the fitted values along the regression line in the original scatter plot. And here are the residuals. So for each midterm 1 score, was the dot above or below the line? Oh, this doesn't look very good at all. So down here, everything's above the line. Everything's above 0. And then in this range, from maybe 10 to 20, it's clear that most of them are below 0. And then it looks like there's a range here from 22 to 30 or so, when most of them are above 0. And then at the end, well, it's hard to tell. That doesn't look so bad to me. Now, it's true that these aren't evenly distributed above and below the line, and so that could be a concern. But my bigger concern is that there are regions along the x-axis where most of the dots are clearly below 0, and then most of the dots are clearly above 0. That looks like a nonlinear relationship to me. So we've done our regression diagnostics and figured out that linear regression is not the right technique to use in order to make a prediction about midterm 2 scores based on midterm 1 scores. So what do we do next? Think about that, and we'll continue in the next video.